Today's topic is going to be 1.8 valence electrons in ionic compounds. We're going to talk about reviewing and writing ionic formulas and talking about ionic bonding. So let's review a little bit about the octet rule. The octet rule is really a rule that stabilizes and establishes an atom so that they're not able to really react that much with other elements. And octet rule by definition is elements like to tend to gain or lose electrons so that they can get a full octet. And the word octet means 8. So as an example, if you take a look at your noble gases on the last column, you will find that they are very, very stable. And the reason is very stable is because of the fact that they follow the octet rule. They have a full octet shell. There are only a couple exceptions with this, and that has to do with hydrogen and helium. Instead of having 8 electrons, they both only have 2. And those 2 electrons only fill the 1s orbital. And that's the reason why they are found in the very top of the periodic table. However, for elements in periods 2 to 7, the full octet is going to fill up 8 electrons, and they're going to fill up the s orbital and also their p orbital. So what ends up saying there is you end up getting 2 for the s orbital and 6 for the p. Now, in terms of the configurations for ions, you basically are going to use the noble gas that is in the previous period. So for example, for sodium, you would look at the periodic table and you would write it as bracket neon. And instead of writing the 1s2, 2s2, 2p6, you can identify that as neon. And that will be 3s1, which gives you the valence electrons. For sodium, the positive charge here indicates that's lost an electron. So instead of having the 3s here, it's just going to have 1s2, 2s2, and 2p6. Metals that lose electrons become cations, and the word cation basically means that they have a positive charge. And in most cases, after they have lost that extra valence electron for sodium, they have a full octet. And that's why sodium is a very reactive metal. Now let's talk about chlorine real quick. Chlorine's a little different. Chlorine actually has an incomplete octet when it's neutral form. It has P5, but if you add 1 electron, it actually makes 8 electrons. And so atoms love to bond with each other or react with each other based off this idea of octet and valence electrons. And so when you're talking about chlorine, it can also, once it gains that extra electron, it becomes stable, which in this case is an isoelectric ion. In this case, it's going to be argon. And so nonmetals tend to gain electrons to become anions, and they acquire that full octet during that process. So as a general rule of thumb, nonmetals are going to be on the right of the periodic table. And this has a lot to do with the fact that they're gaining electrons, while metals are losing electrons, and these are on the left side of the periodic table, with the exception of hydrogen in this case. And what you'll see is a staircase, which is the separation between nonmetals and metals, and those are called your metalloids. Now let's define ionic bonding. Ionic bonding means that you are actually transferring electrons from nonmetals to metals, forming a bond between them using what they call electrostatic attraction. And the word electrostatic means that there is some sort of charge that gets put in. And this charge really is determined by the fact that these electrons are swinging back and forth. And so generally what you'll find is cations or metal ions and anions usually form these bonds based off of the opposite charges. So it's very similar to like a magnet. You'll find the positive and negative charge kind of combining together, and these are going to form what they call polyatomic ions. So let's go ahead and jump into ionic bonding. So ionic bonding here for sodium, it has a little blue dot here. This represents its valence electrons. And chlorine here, these green dots represents its 7 valence electrons. And sodium is going to give that electron to chlorine. When it does that, it's going to have a positive charge, and chlorine is going to have an excess negative charge. Now, when they combine, they form salt. And that's the reason why salt is neutral. It's because of the fact that the positive charge, the electron from sodium, has been given to chlorine, and chlorine now has a stable octet. Now here's another example for calcium oxide. So calcium oxide is 2 electrons for calcium, 6 for oxygen. So calcium wants to give away 2 electrons. And when it does that, it forms 2+. However, oxygen because it received those 2 electrons, forms 2 minus, and you get calcium oxide as a solid. And usually ionic bonding most of the time forms solids, not all the time, but most of the time they form these solid structures. Now, how to recognize ionic compounds really depends on the fact that you have a metal and a nonmetal, or what they call polyatomic ions. The word poly means many, and obviously ions means a charge. So the first word in the name of the metal or of that one is basically going to give it its name. And it's usually going to be an ionic compound. So in this case, it could be a metal, or in some cases, ammonium. Now, binary refers to 2. So when we're talking about ionic compounds, you have the positive cation, which is written first. That's going to be the name of the element. And your negative ion is going to be written last. In this example here, you're going to change it to IDE. So it's going to be, instead of being bromine, it's going to be called bromide for anions. Now, another thing is some metals can form cations with different charges. And so usually we put Roman numerals for those. So as an example, what you have right here is copper could be Cu2 plus or Cu2 plus. And that one we'll call it as copper 1 sulfide or copper 2 sulfide. So if I use the Roman numeral 2, what that represents is that it's a 2 charge. So that's another way of kind of writing it out. Another example is iron 2 and iron 3 plus. In this case, iron 2 has lost 2 electrons, so it's an iron 2, and iron 3 has lost 3. So in this case, it's going to be iron 3 oxide. In this case, we have lead 2 and then lead 4, again, losing those 4 electrons, and then those 2 electrons gives you different types of lead. Now, polyatomics are a little bit different because polyatomics do not have IDE. So in other words, if I take a look at this one, CO32 minus, that's called carbonate. So we don't change the O here to carbon oxide or anything like that. We just use it as carbonate. In this case, we use calcium carbonate. And again, there's going to be several names that are going to be associated with that as well. Now, only 3 of them have IDE, and that's cyanide, hydroxide, and peroxide. So if you see these right here, even though it may look like they're binary polyatomics, they're considered to be polyatomics, even though they have the IDE. So those are the exceptions to the rule. Everything else is considered to be a monatomic anion if it does have the IDE ending. Ammonium is the only polyatomic cation that you need to know for this class. So NH4 is the only cation that is a positive charge. Majority of all the cations are going to be metals. And so here's an example. NH4Cl is called ammonium chloride. NO3 is your nitrate ion. So if you were to put these two together, you call it ammonium nitrate. So not nitride because of the fact that this is a polyatomic ion. Now, how do we write the ionic formulas? The way we do them is that they always must sum up to a 0. So if you put the ion charges in and you put them together, they all must add up to a 0. And the charges always come from the group of the periodic table or a list of them. So if we take a look at those and we put some parentheses, you should be able to see what those polyatomic ions are going to be. And so here's an example. Let's take a look at calcium chloride. Calcium is a 2 plus charge. It's in group 2 of the periodic table. The IDE in this case tells us is a monatomic ion, which comes from chlorine. And when you put chlorine in there, chlorine's always going to be a -1 from group 7, and it's going to be called calcium chloride. And usually what we do is we put what we'll call the crisscross method. Crisscross method is you put the ion charge on top. So in this case, because this is calcium in the group 2, and chlorine is 1-, you're going to bring the 1- down here, and you're going to put the 2 down here, and that gives you calcium chloride. And that basically is because of the fact that it is in a different group. Chlorine is in group 7, and then calcium is in group 2, and that basically gives you your charge. All right, let's still look at iron 3 sulfate. Iron 3 sulfate has a charge of 3+, and in this case, we write it down as Roman numeral 3. And you know that sulfate is an SO4 2- because of the fact that you memorize it. So you do have to memorize some of these charges because these charges kind of tell you what that's going to look like. So a 2- indicates that that's a 2- charge, and then iron 3 is a 3+. Now again, as a crisscross method, we always put parentheses on the polyatomic ion. So in this case, SO4 is a polyatomic. So we bring the 3 down, and then the 2 comes right down here just to indicate its balance. So if you actually multiply out the numbers, 3 times 2 gives you 6, 2 minus 1, 2 minus gives you 3, times 3 gives you 6 as well, and that would be the balance formula polyatomic ion for iron sulfate. All right, so let's go do a couple of them here. Let's pause the video and take a look at, if you can write these ones down: aluminum sulfate, iron 2 oxide, and so on, and see if you can identify the charges that go with them. There's going to be a pure ion sheet that you will have all of those polyatomic ions in there. Make sure you kind of get to know those really well. So the first one is going to be aluminum sulfate, and sulfate is written as SO4-3. Aluminum is Al, and again, you do the crisscross method because aluminum has a positive 3 charge and sulfate has a -2 charge, so that kind of brings it down. Now iron 2 oxide is going to be the exact same thing. We know this is an iron +2, and that's a -2, so that brings us with FeO. Now we want to reduce this down because normally when you do this, it will come out as Fe2O, Fe2O2. Divide both sides by a 2 and you get FeO. Iron 3 oxide is a little different. Iron 3 oxide is, again, we're going to drop down that 2, but again, the same process. So our answer should be Fe2O3 because iron 3 is a 3+ charge. Strontium fluoride is going to be Sr, and strontium is going to be 2 charge because it's in group 2, and fluorine is -1, so that gives you SrF2. And potassium chloride is KCl, which is going to be +1, -1. And then ammonium nitrate, which is again going to be a +1, -1, you crisscross them, you end up NH4, NO3, and then lithium sulfide, which is -2 for sulfur and +1 for lithium. And that brings us to Li2S. Now, here are the ones you have to memorize and make sure you understand this idea. Usually group 1 is going to all have +1 charges, but they're also going to be a -1- for hydrogen. For group 2, you have 2 positive charges. Now, if you go across from left to right, you could see that there are 3- charges here, 2- for the anions, but then your transition metals can actually have more than one because of the fact that they have multiple charges. So in order for the octets to work, the charges on the anions and the cations, they must equal so that you can actually fill up those octets. And again, the reason why we have these positive charges is because of the fact that they want to fill up that octet. Same way here, they want to fill up that octet. And the charges in the most of the cations are equal to the number of electrons that must be lost to acquire that full octet. Charges on the ions are usually related to the group they're in. So again, going back to group 1, it could be also 1-, group 2, D blocks are 1 to 5, and then 3, 4, and then 3- and 2, and then 1. So starting with group 5, it turns negative where you have your nonmetals. And then obviously you get your positive ones where they are your metals all the way up to group 4. Now, taking a look at your ionic formulas by group, you can tell that for group 1, they're always going to be, the cations are going to be, in this case, on the left-hand side, and your nonmetals or your anions are going to be on the right side. And so as you can see from here, you could see that when you crisscross them together, you can get different combinations depending on what that charge is. So in this case, I need 2 lithiums to balance out the oxygen. While here, I only need 1 and 1. Same way with this side. For group 5, you can also bind group 5 with group 1, and so lithium nitride, sodium phosphide, etc. And you could also bind group 2 with the nonmetals on 5, and then 3 with 5. And so as you can see, you actually drop them down from a 3 to basically 1s.